Right. So our next topic is central forces. Here we consider the forces applicable towards a point or away from a point. Symmetric about a point, like some forces acting starting from a point, all directions with equal magnitude. Some kind of like nuclear forces, like the attraction between a nucleus and an electron, or attraction between planets. So these things can be explained by these central forces, where a fixed point of observation is well defined. Okay. So, and coming to Newtonian mechanics, the basic Newton laws of motion are defined for point objects. So we need to deal with rigid bodies. So basic Newtonian mechanics is defined for point objects. So now we need to extend this to rigid bodies. This is the main agenda of this central forces or rigid body dynamics. So we need to identify a point where the entire properties or at least mass of the object is concentrated in a rigid body. So we need to treat the entire rigid body as a point object. So we need to identify a point where the entire mass is focused to be existing. So this we need to define to apply Newtonian laws of motion to rigid body systems. Okay. And the first observation that comes here is, let's say, you have 2-3 points. Let's say R1, R2. There are 2 points. I'm considering the basic model, and that contains 2 points. I need to identify a point where the actual mass is focused. Let's say m1 is the mass of the first object and m2 is the mass of the second object, and locations are given by r1 and r2 from the origin. And we need to identify the location of R where the entire mass of the system seems to be concentrated. Okay. So the total mass of the system is m1 plus m2. And here we define the moments of the mass. The first moment means multiplying whatever physical quantity with the distance from the point of observation. So the first moment of mass is given by m1 r1 plus m2 r2, and that will be equal to total mass times r. Okay. Right. So to deal with this rigid body systems and to apply the Newton laws of motion to rigid bodies, we need to convert this rigid body to a point object. So that is why we took a basic system of 2 point objects and defining their locations as r1, r2, masses are m1 and 2. R is the center of mass, where the entire effect of the object can be treated as a point object. This is the point where entire mass seems to be focused. So now first moment is given by mass multiplied by the radial distance from the point of observation. So it is m1 r1 plus m2 r2, which is equal to center of mass case, total mass multiplied by center of mass. And from this equation, R is given by m1 r1 plus m2 r2 by m1 plus m2. That is the center of mass of the system. Okay, and if you consider second moment, it is m1 r1 square plus m2 r2 square equal to m r square. Okay, and we need to develop this equation further. The issue is so I'm defining another set of coordinates here. Let's say that defined as let's say this total distance is r. Total distance is r, and distance from center of mass to first object, let's say this is r1 and this is r2. From center of mass. So I need a different notation for this. Okay, so R is equal to R1C plus R2C. Then so the distance of the first object from center of mass. How to get that? And this R is given by okay. So here this R1C is what? So what is that happening? This is R1 and this is R1C. So R plus R1C is R1. R plus R1C is equal to R1. So from here R1C is equal to R1 minus R. Okay, so what is that? R is equal to mr1 plus mr2 by m1 plus m2. So R1 minus mr1 plus mr2 by R1 plus R2. So this is sorry, m1 plus m2. So m1 R1 plus m2 R1 minus m1 R1 minus m2 R2 by m1 plus m2. So what do you get? m1 R1 gets cancelled. m2 times R1 plus R2 by m1 plus m2. So what is that? R1 minus R2, vector difference. R1 minus R2 is R. So this is R1C. Length of the vector from center of mass. Distance from center of mass to the first object. R1C is M2R by M1 plus M2. The same way, if you continue, R2C is R2 minus R, which is M1R by M1 plus M2. So that is the distance of the second object from center of mass. Next one is equation of motion. Force is given by so this double dot is the double derivative. M1 t square R1 by t square is a double derivative. And second equation. So they are the force equations. And from this, so R1 double dot is F by M1, R2 double dot is F by M2, and R double dot is R1 double dot is R2 double dot. So which is F by U. And that is called the reduced mass of the system. So here comes a negative sign. Because we are considering the distance from the center of mass. So from the center of mass, R is downwards, R1C is also downwards, and R2C is upwards. It is in the opposite direction to R. So the force equations will include a negative sign here, the second case. Okay. So total R double dot, which is the double time derivative of R, is equal to R1 dot minus R2 R2 dot, because we have this here, R is equal to R1 minus R, and if you take double derivative, you get that. So this is called the reduced mass of the system. Here is a minus. This becomes plus. Already there is a minus, I am subtracting. Okay, so that's called reduced mass of the system. And if you take any set of this physical quantities like moment of inertia, is equal to mr square plus mu r square. And in the same way, kinetic energy P1 square by 2m1 plus P2 square by 2m2 is equal to P square by 2m plus small p square by 2m. So these are the main equations that describe the properties of central forces. This is called that is called parallel axis theorem, which is the moment of inertia of individual objects will be in a rigid body will be equal to moment of inertia of the center of mass plus moment of inertia of rest of the body with respect to center of mass. In the same way, the kinetic energy of individual particles will be equal to kinetic energy of center of mass plus kinetic energy of rest of the object with respect to center of mass. If there is any moment with respect to center of mass, that will be considered. If it is a strictly rigid body, there won't be any moments. Kinetic energy with respect to center of mass may be 0 for a perfect rigid body, whereas this moment of inertia with respect to center of mass has a valid value. This is what we use in compound pendulum, which is a extension of simple pendulum where a point object is replaced with finite size of the object. So there we have to consider moment of inertia of center of mass plus moment of inertia of rest of the object with respect to center of mass. So this is a simple extension for Newton's laws of motion, where the motion is considered with respect to center of mass. Motion of the object of rigid body will be equal to motion of the center of mass plus motion of the rest of the particles with respect to center of mass. So that is the essential take-home message for this from this discussion. So these are simple derivations that we'll see in the next session, how to arrive at those equations of parallel axis theorem.